Hello everyone. So today I'm going to talk about Minimax, and the reason I would learn about it is because at General Assembly, so I complete a course at General Assembly, and for us the first project will be about doing a tic-tac-toe, and then at that time I make something more complex and I try to implement AI. And at first I use my own, I self-build my AI for a simple tic-tac-toe, and then the instructor there uh, told me something about Minimax. So because today is a Ruby meetup, so I also uh, have converted the games to Ruby. So for the game is the goal is to so for the game the the goal is to win three. There are 9 local bots, so the goal is to win 3 local bots in a row to win. And then in this game, we can use something called Minimax. So for a very simple game, you can just explore all the move, and you can explore all the move to the bottom, and then you will find out whether you will win the game or lose the game or draw. And here, for X, he will have 3 possible moves to make. So one is here, another one is here, another one here. So for here, X is a maximizing player. So if the bot makes him a win, then it will be a positive 10. But for player O, it would be a minimizing player. So he want to get a negative score. And actually, the score is not for the player. It is for the bot itself. And one problem for this tree is X can win the game fast or win the game slow, but this algorithm still give the same score. So in some cases, the AI algorithm will just give up the game because he knows that it knows that it will not win the game, so it just give up, just make some stupid move because it knows that it will not win. So for this algorithm to make it better, we can put some more score. For example, here, if the game can be finished fast, then for example, it should be 12. So both X and O. So for O will avoid avoid ending the game so fast, but for player X, it will try to finish the game fast. But then, because this is a simple game, but if we talk about something more complex like chess, it will be too many branches to explore. So there will be a problem because we don't have unlimited computational resources. So we need to find a way to let AI to explore as deep as possible. So that's why we need to set a depth limit so that we will not use up all the computational resources. So for here, there are some score here, but actually down below there are much more looks, and it's not reaching the end of the game yet, but we need to have some score somehow. That's why we have something called bot evaluation. So actually it's involve both objective judgment and subjective judgment. So for example, for a, oh, for a game like this, the center local bot is more important. So that's why number 4, index 4 would be higher here. 0, 1, 2, 3, 4. Yes, here. So the local bot, the one in the center will have higher weighting. And then in each of the local bot, each of the square will have different score as well. That's why the corner one would have higher score than the one on the edge, and the center one will have higher score. And then we have some combination. So If you have two O in a row, it will be in favor of player O and something like that. But there's still a problem is because we still have a depth limit, and actually we want the AI algorithm to go as deep as possible. In order to do that, we should try to try not to explore meaningless try not to explore meaningless branches. So for example, this is a photo I got from Wikipedia, but actually I think this is a little bit confusing because for this look, it actually means it's not yet explored, but in this photo, it's already showed the score here. So that's why I cover all the number here so that you will not get confused or misled. So this is called alpha beta pruning. So for maximizing player, he will need to choose the bigger number, and for the minimizing player, will choose the smaller number. And so for this level, the minimizing player will choose one of these two numbers, and 5 is smaller. So that's why he will pick 5. And when we explore the game tree, we will go from the left, it's like this, and then to the right. So we will explore from left to right. So at first, minimizing player get number 5 here, and then maximizing player will get this 5 from here. So for alpha beta pruning to work, at first, alpha is for maximizing player and beta is for minimizing player. So at first, alpha would be negative infinity and beta would be infinity. So after minimizing player get 5, beta will become 5, and alpha would be negative infinity here. So each of the looks here would, at first, originally would be alpha as negative infinity and beta as infinity. So now 5 is a beta, and then maximizing player get the 5 from here. So now here, alpha would be 5, and beta would be infinity. And then we go to this loop, and then minimizing player get 4 because 4 is smaller than 7. So here, beta will be 4, and then it will get the alpha from the loop above. So the alpha would come to here, and alpha would be 5, and 4 would be the beta. And for alpha beta pruning to work, we will not explore other branches when alpha is greater or equal to beta. So now alpha 5 is greater than beta 4. That's why we don't need to explore the minimum, the branches left here. So I think it may be a little bit confusing because I also don't fully understand. But at least this is how I can explain it. And I can give an example in real life is, so if you're a chess player, if you're a good chess player, you can think several moves ahead. And then, for example, for a simple game like tic-tac-toe, it is in a real life. Imagine you are a good chess player, but this is a small game. So I think many people can think several moves ahead. And there are sometimes you can think of some possible moves, and then you will think about if you make that move, how your opponent will react. And based on that, you can, for example, you have 3 possible moves, and first you explore the first move, and then you analyze it and get enough information, and then you analyze the second possible option, and then maybe you don't need to go deeper. You don't need to, maybe you just need to think 3 steps ahead, then you already know that it's not a good move. It's not as good as the first one. So for the first one, you have already think 7, for example, 7 steps ahead. But for the second option, you already know, you already make a conclusion that you don't need to think so many steps ahead to know that it's a stupid move. That's why you don't need to waste your time or effort to think so many steps ahead, but you still know that it's not a good enough move. So for alpha and beta pruning is something like that to work. And one thing I need to pay attention is the score is not for any of the player. The score is to reflect the board. I think it would make me confuse easily because uh, we learn what score is since childhood. We usually learn about what score is when we play sport or when we take exam. So the score is for ourselves or for our team or for other team, other people. But for the score here in Minimax, it's not for any of the players. It is for the board itself. So I think to make this keep in mind, then it would be easier to understand what Minimax is. Yeah, so this is the game I built in Ruby. And for example, like this, then the AI will make this move. Oh, yes. So the AI is making his move. Okay. Thank you for listening to this presentation.